Thank you very
Andrea
much.
Diercke, so I hope I pronounced it correct. Diercke, okay. Universal method for solar filament detection from H-alpha observations using semi-supervised deep learning. So please, take your time.
Yeah. So, yeah, it was already introduced, so I can already start. Yeah, I'll just start with a brief introduction to filaments. Filaments, when you see a chromospheric image, the most omnipresent feature in these chromospheric images, at least in H-alpha, are filaments. And these are cool plasma structures sustained by the magnetic field. As you can see here, they are really cool features, actually. And they form above polarity inversion lines, so separating between different magnetic polarities. And when you see them in high resolution, as here from the SST or the Big Bear Solar Observatory, you see that filaments are actually collections of single threads. They are best visible in H-alpha, but you can also see them in EUV images and helium 10830 or calcium 8542 angstrom, and you can do a lot of interesting research with them. They are really dynamic. You can track the flows and see the different Doppler velocities in the filaments, how they are formed, and when they are connected to the magnetic field, and when there are changes in the magnetic field, then also they can erupt, like here in coronal mass ejections. And when a coronal mass ejection is erupting, then it's even can be even geoeffective. Furthermore, filaments are related also to the solar activity cycle, so they are a proxy for the solar activity cycle as well. For active region filaments, which form in the close by in active regions, then it's obvious they are following the sunspot cycle also, but there are also polar crown filaments which form at the border between the unipolar field at the poles, and there's also a cycle which is a little bit offset to the normal sunspot cycle. So at around minimum they form at mid-latitudes, and towards the maximum they form closer to the poles, and also there you see then here this rush to the pole on both sides for polar filaments. And this is exactly what I'm interested in my research, and why I started this study actually. But in total, what's missing for filaments is a reliable and complete catalog for filaments, which would enable much more research, and where you could perform certain analyses much faster. Here a little bit more to my motivation. Like I said, I wanted to track polar crown filaments, and therefore I used H-alpha maps of a small full disk imager called Crotal. I will introduce it later. And used classical morphological image processing, in this case on Carrington maps, created from the full disk images, and tried to extract then filaments. Since I was interested in polar crown filaments, which are usually quite large, as you can see here in the bottom, I selected just the larger filaments to be able to differentiate between filaments and sunspots. This caused the problem that I was also neglecting small-scale filaments, which was okay for this study, but in general, when I want to do some statistical analysis of filaments in all scales on the sun, then I want also to include the small-scale filaments, which I neglected here in the morphological image processing. And furthermore, morphological image processing is very slow, and more processing steps are needed, and it's not applicable. The same method is not applicable between different H-alpha image sources. So what we wanted to have is a universal method to select filaments in H-alpha data, and therefore we tried it with to train a neural network, and then also use or get the segmentation maps from this. The idea of our method is in this case that we label the crotal data, H-alpha full disk data, by hand, and trained with this the YOLO version 5 object detection algorithm on the crotal images, and used then the trained YOLO object detection network to label GONG data, which increased then our data set by a lot. And with the combination of GONG and crotal, we then created segmentation maps. So YOLO is giving us bounding boxes, and from these bounding boxes, it's much easier to get then segmented filaments, which are then the input maps for the unit for the training, which is then trained on GONG and crotal together. So for first introducing the both image data sets, the one is crotal, the other one is GONG. Crotal is a 10 centimeter aperture telescope on Tenerife at the balcony of the Vacuum Tower telescope. It has a resolution of about 0.96 pixels, and in comparison to GONG, which has a much smaller aperture, but about the same pixel resolution. So in principle, GONG has a pixel resolution of about 2 arcseconds, but with some camera sampling, the GONG team achieves a pixel resolution of about 1 arcseconds as well. But you can see also they have more or less the same full width half maximum on the filter. They look quite different. So in crotal, there's a lot of more fine structure visible in the images. I don't know if you see this on the screen, but then in GONG, and yeah, they are a little bit different from the feeling also. For crotal was operated between 2012 until 2021. And they're on 1,062 observing days, and we labeled all the data between 2012 and 2018, which are 962 images. For GONG, we used then the complete data set between 2010 and 2022, but with a cadence of 4 hours. So every 4 hours we have one GONG image, which was then labeled by the trained YOLO network. First of all, we needed to do some more data processing. For crotal, we selected the best image per day with median filter gradient similarity. And for GONG, we used the quality assessment by Robert Jarolim, who optimized basically this quality assessment with neural networks. Both image data were normalized to median intensity and limb darkening corrected, and then we used a method to approximate these intensity changes in the crotal images. This is the intensity changes in the normal images are not really visible, but when you have it in a very small range, then they are really there.
Andrea, please move towards the conclusion, because we need to have time for questions.
Yes, and so with Diercke polynomials, we modeled then these intensity changes, and we also used it on GOG data, and reduced then the resolution of the images to 10K. For the object detection algorithm, here on the left side you see the ground truth with the bounding boxes, and on the right side then the predictions from the YOLO network, and they are very similar. But you can see YOLO is sometimes grouping drawing the bounding box a little bit different than how I label the data in the images here. But most of the filaments are detected. Sometimes you have more filaments detected by YOLO than they were labeled in the ground truths, but sometimes also filaments are missing, especially very small ones. But overall, it's a very good result here already. Then these are the results from the segmentation, where here's the enlarged figure, and there we see in this case the sunspots are excluded in the detection, in the segmentation here, but sometimes you have here false detection. This is not a filament, most probably, and maybe here one penumbral filament is detected as a filament, which is not an actual filament or not. But overall, you get really good results here. Here are some more nice results of filaments. Here's a polar crown filament, where I'm very happy that this is working very good on the polar crown filaments, and even these large filaments are also nicely tracked. To evaluate this, we compare, so the ground truth, we have only bounding boxes, so we created from the segmentation maps also bounding boxes, and we compare, these are the red boxes, and the yellow boxes are the morphological image processing, which I showed in the beginning, and there we also created the bounding boxes for the mass from the morphological image processing and compare them. And you already see that there are much less detections in the morphological image processing. And here we quantified this more or less. So we have here the intersection over union for the ground truth compared to the YOLO predictions, ground truth compared with the segmentation results, and the ground truth compared with the morphological image processing. And we see that we get very high values, mean values for the intersection over union from the ground truth and YOLO. It's a little bit less for the segmentation method, but it's also how we create the bounding boxes. Most probably that there are still some problems how we define the bounding boxes in the after the segmentation. But the visual inspection is anyhow really promising. And also the accuracy is very high for the segmentation results compared with the ground truth. And also precision and recall achieve very high values here. So we are very happy, especially compared to the morphological image processing with our results. And we will test also the algorithm on another H-alpha full disk imager, which is from the Kanzhö Solar Observatory. And with this, we can then provide reliable filament segmentation catalog with a cadence of 4 hours from the GONG data. And I hope this then enables a large variety of new, cool filament research. So, thank you.
So, Andrea, I thank you personally. I think everybody is ill for a really interesting talk. So, it looks like we have the next speaker who was supposed to be online is cancelled, so we have time for more or less relaxed and thoughtful discussion. So, any questions, please? Okay, we have a question in the third row. Yes.
I can share it. Oh, there we go. Thank you. That was, really interesting, as like I said. But the bounding boxes, let me try and understand if I got you correctly. You use YOLO to get bounding boxes.
Yes.
And you use those bounding boxes to make segmentation masks to train UNet. Is that it?
Yes.
Do you mind saying a bit more about how you get the segmentation from YOLO? Is that more manual or?
This is manual. This
Okay.
is with thresholding. Then, yeah.
And then a follow on, is it each individual bounding box is an input to the UNet, or is it the whole sun?
The whole sun, and so the input from UNet are segmentation maps. And these segmentation maps are then created from the bounding boxes we have from YOLO.
Okay, cool. Thank you.
Sorry, just a quick comment to this as well. Maybe to explain the reason why we did this in that way. When we do the thresholding for the individual boxes, we get a lot of noise. So we get additional segmentations that are not included. But if we apply it then to UNet, it's basically just noise in the data, while the focus is on the filaments. So if we then retrain the model for this segmentation, like with the thresholding method, it will ignore those noisy parts of some of the bounding boxes in the end. And this is the advantage that we get from this. That's kind of the idea.
Excuse me, I have actually a question to your comment. Could you please give back the microphone? By retraining, you mean start training the model over again, or you mean training pre-trained model with less noisy data? Because that's important issue.
So it's kind of what we get then for the UNet input is kind of noisy to some extent. But it's more like random noise. So we count on the ability of the neural network to generalize to the filament detection, which is much easier than replicating some artificial incorrect labeled fragments, basically. So this basically originates from the fact that we have always like certain boxes, and there the threshold can just fail. But this is more or less like random. So when the UNet learns basically from all the data samples, it's very difficult to reproduce this noise factor. And this is what is then missing. This is exactly what we want, that we get this reliable filament detection out of it at the end. Does this kind of answer your question?
Yes, it does. Thank you.
Okay.
Any more questions?
There is a question online.
Yes, we do have a question online. Daniela Lakatos, please.
Hi, very nice presentation. I have a question. Could this model be applied to any other data sources except H-alpha? And how complicated would it be to retrain it on something new? So I was thinking that maybe you could also apply it to something like AI304.
In principle, yes, but since especially for YOLO, we used a labeled data set. So we first have to label then the 3 or 4 data, and then it would work the same way probably. Then.
Okay, because there's much more data in AI that you could use for tracking the evolution of filaments and stuff like that.
Yeah, that's true. But in H-alpha there are also some smaller filaments which are sometimes missed in AIA data.
Okay, thank you.
Second row, please.
It was an interesting talk. So the thing is that I was planning to use YOLO to do CME detections and like active region detection. So I know a little bit about it. So YOLO is a pre-trained neural network which is trained on certain data sets like COCO dataset. And so you used a pre-trained neural network to train the...
No, we trained it newly with our data.
Right, so creating labels and
Yes.
these bounding boxes.
Yeah.
So, okay. And the other question was, you used UNet to do segmentation.
Yes.
Can you use YOLO to do the entire thing? Because as far as I know, YOLO is like a complete architecture where you can have convolution layers, and then you can do segmentation and classification as well.
But as far as I know, YOLO was supposed to just give you the bounding boxes, provide you the bounding boxes, and not the segmentation itself.
Okay.
So the segmentation has to be done by another step.
Right. And do you think that there is any other method to do segmentation other than UNet?
There are a lot of different...
So why UNet fits here?
It worked. So we just used it because it was working in our case. So it was very reliable, and I think UNet is used in many different fields for segmentation and
Yeah, I agree. Thank you. Thanks.
Well, actually, here I want to give some little bit to comment on your question. Well, actually, the thing with UNET, because over the last 3, 4, 5 years, it's proven to be really one of the most efficient image segmentation techniques, and mostly important that it performs pretty well on relatively small training sets. So indeed, maybe there are no alternatives, I would say, in this situation, maybe. So any more questions? Well, I do have a few questions, actually. Regarding UNET training setup, what was the size of the training set?
We had 70% of the data, so it's about 18,000 GONG data as input plus the 1,000 Croter data, so 70% from this, then 10% for the validation set and 20% for the test set.
So it was kind of order of tens of thousands images.
Yes.
Tens of thousands images.
Yeah.
And so that, roughly speaking, we can assume that it's maybe a few tens of events with I don't know, few tens of images in them, or so roughly how many events?
Since GONG and also Crotel covers the complete solar cycle, we have images with a lot of filaments during the maximum of the solar cycle, and also images where no filament at all in 2020 when there was the minimum or so. And so it's a quite complete data set, so you have really images with no filament and images with thousands of filaments in the data.
So okay, but in that case, if, as you mentioned, with such variety of data, any concerns that actually having such a large train set with all sorts of the data there, that it's actually making your model more biased than, for instance, if it would have been like 300, 400, 500 images, but pre-selected visually, so to say, to be sure that the data at least isn't noisy. So any concerns about it? That's
at least for the test set, for instance, we were selecting from each year 1 month, consecutive months of observations to reduce some biases in the data, and to take this month out from the training set and also have it then for the test set as a consecutive month, and this may also help with the validation.
Okay, and so, thank you very much. Okay, it's interesting. And regarding labeling masks manually. So
it was we were 3 persons labeling the complete Crotel data set by hand, and
so but you were rather labeling the segment of the image, but not the shape of the mask precisely. Is that correct?
No, just bounding boxes. So we were pressing basically 2 times to indicate the corners of the bounding box, and then and this was basically then our input, and for each filament in the H-alpha images. So I don't know.
Maybe you can list a little bit back.
Yeah,
I have to keep it then, because I thought. Okay, so well, actually, I think we do have how much? We have 10 minutes till the next talk. Anyway, we have another question.
So here's a question. I saw your method and it is applied to H-alpha images. Is the method cognizant of the fact that it recognizes filaments, or is it agnostic to the structures that it tries to recognize?
Since we are excluding sunspots, we are quite, so you see that sunspots are excluded in most cases. And we have all different types of filaments. Sometimes they are really long and elongated, but sometimes you also have, especially for polar crown filaments, just single blobs basically of plasma, which are visible like this in H-alpha, and they're still recognized.
So in essence, if you tried an EUV image, would the same method be able to identify coronal holes as well?
since it's labeled with our filament data, not immediately, so you would need probably then the labeled coronal hole images for this.
Okay. Okay, and then, I mean, besides the identification of filaments, there is certain physical information that you can extract, like the spine of the filament,
Yep.
the barbs of the filament, the chirality of the filament. Does the method do this at this time, or you need to, you know,
These are more
develop
processing
further?
steps then, but
Okay.
with the segmentation maps, it's then very easily with some blob analysis or something to then extract certain features like the tilt angle of the filament, the size, or also then the chirality as this point. But I think the next talk is about this, even the chirality of filaments, and yeah.
Okay, thank you.
So, many thanks. And well, actually, I propose to continue the discussion informally afterwards because, yes, looks like there are so many questions from different people, and we need to move forward. So, yeah.